All right, so I'll call this section 13.4. It's the fourth topic that we've talked about in probability. And we're going to talk about compound probability. So compound probability, we worked with compound probability a little bit yesterday when we did Mr. Spiffy's ties. So it has to do with more than one thing happening. So let's talk about what a compound event is. Now let's turn that off, please. So compound event, it just means an event made up of more than one thing. An example of a compound event from what we did yesterday with Mr. Spiffy's ties was the probability that Mr. Spiffy wears a striped tie and then a plaid tie. So we're talking about two things, one thing after the other. So that's a compound event. On the back, the last several problems had several compound events. Another example would be rolling 6 on a die and picking a king from a deck of cards. That's a compound event because we're talking about two things. So we're going to figure out how to calculate probabilities with compound events. And there are several kinds of compound events that we need to worry about. The first set that we're going to talk about is independent events. And independent events, pretty much like they sound, one doesn't change the other. One doesn't affect the other. So an example of independent events would be the one that I talked about before, rolling a 6 on a die and picking a king from a deck of cards. Rolling the 6 doesn't change my pick from the deck of cards at all. So what's that? When we'll talk about dependent events in just a second, and then we'll talk about what would change. So one's not going to. So I'll give an example with the deck of cards for dependent events, so where one changes the other. So independent, just like they sound, one doesn't change the other. Dependent, it's just the opposite. One does change the other. So we had some dependent events yesterday in Mr. Spiffy's ties. Once he stopped putting his ties back in the closet, then the probability turned into dependent events because he had less ties to pick from, and they were less of a certain kind because they weren't in the closet anymore. So once he took one out and didn't put it back, that made the probability the next day different. So that's an example in Mr. Spiffy's ties of dependent events. An example of a deck of cards is picking out a king and then picking out, without putting the king back, then picking out an ace. When I don't put the king back, I don't have 52 cards in the deck anymore. I only have 51. So I have less total chances in my deck of cards. So that changes the probability of the second thing happening. So those would be dependent events. Lindsay, you with us? Mm-hmm. Are you sure? Yeah. So dependent events, one changes the other. So the example I gave, picking a king and then picking another card where we don't put one back. How about tossing heads on a coin and then picking a 2 from a deck of cards? Are those dependent or independent? What do we think? Independent. Flipping the coin doesn't change what happens in the deck of cards. So those would be independent. And then how about picking a king from a deck of cards, not putting it back, and then picking an 8? Dependent, independent? Dependent. Not putting the one back changes the probability of the second. So now we need to know how to calculate probabilities. We know what they are. Let's calculate probabilities. So probability of, we'll start with independent events. So we're going to say our two events, A and B, are independent. Probability of A and B together. So the probability of Mr. Spiffy wearing, or let's see, probability of, we need independent events, probability of flipping a heads and rolling a 6 on a die. Probability of A and B, we multiply. Probability of A times probability of B. So for independent events, we multiply probabilities. So let's look at an example. So we're going to roll a die. We want the probability, we want to know what's the probability of rolling greater than 3. And pick B from a hat with A, B, C, D in it. So we have slips of paper that have A, B, and C and D. So we have a die, we want to figure out the probability of rolling more than a 3 and picking a B. So rolling the die doesn't change what happens in the hat. So these are going to be independent. So we're going to multiply our probabilities. So I'm going to just make a note that these are independent. Because rolling the die doesn't change the pick from the hat. It doesn't change it at all. I can roll the die and pick from the hat, and one's not going to change the other. They're not connected in any way. So these are independent, so we're going to multiply. So first let's find the probability of, and I'm going to write greater than 3. The probability of greater than 3 on a die. How many favorable outcomes do we have? How many numbers on a die are greater than 3? 3? We have 4, 5, and 6. So our favorable is 3. How many total do we have? 6 on a die. And I'm going to reduce this, so reduce that to 1/2. And what's the probability of picking a B from the hat? How many favorable outcomes do we have? 1. We just have 1 B. Total? 4. So the probability of greater than 3 and B is 1/2 times 1/4. And when we multiply fractions, we multiply straight across. Multiplying fractions, we multiply straight across is 1/8. So probability of greater than 3 and B is 1/8. Yes? Right? Yes, we'll talk about that in just a second. Very good question. So you're asking about dependent events. How do we figure out dependent events? Because if we take a letter out and don't put it back, then that makes it a dependent event. We'll talk about that in just a second. Okay? All right, questions on this? So with independent events, we multiply the probabilities. If one doesn't change the other, we find the probability of one, find the probability of the other, multiply them together. Dependent events. We're going to use the same idea, but it's almost the same. There's just one little twist. So A and B are dependent. So whatever happens with A changes what's going to happen with B. So probability of A and B, so we're looking at the two together, is a probability of A times, we're still going to multiply, but we have to calculate the probability of B after A happens. So we still multiply. Our second probability is after the first thing happens. So we have to calculate the second probability after the first event. So an example of this would be Mr. Spiffy taking a tie out of his closet and not putting it back. So if we wanted to figure out the probability of him wearing a plaid tie on Thursday, he's already taken several ties out of his closet and not put them back. So that's going to affect the probability. So we have to find the probability of, say we want the probability of a striped tie on Monday and a plaid tie on Tuesday. On Monday, he takes the tie out and doesn't put it back. So we have to calculate the probability of that. Probability on Tuesday has to be after he's not put the tie back in the closet. So that would be a dependent event. For the hat, we would have to, if we took out the B, and then we wanted to find the probability of A, we still have one favorable because there's still only one A in the hat, but now there are only three to pick from. So the second probability would change after we did the first thing. And we'll do an example of that, of this right now. So we're still multiplying. We just have to find the probability of the second thing after the first thing happens. So our example, we have a bag with marbles in it. Marbles, bag with marbles is classic probability problem. So we have 5 red, and I'm going to use shorthand, 5 red and 6 blue. 5 red and 6 blue. We want to find the probability of blue then red. And we're not putting the first marble that we pick back into the bag. We're taking it out and holding it in our hand. Because we don't put that marble back, it makes it a dependent event, because then there are less marbles in the bag. So there are less total marbles. So this makes it a dependent event. So we have to calculate our second probability after the first one happens. So let's find our probability of blue. So in our bag, how many favorable outcomes are there? How many blue marbles? 6. And how many total? 11. And I'm going to, this is good, so we can't reduce this. So now we're going to calculate our second probability, probability of red, after blue is already picked. So our favorable, how many reds do we have? 5. How many total? 10. We only have 10 left. That's what makes it dependent. It changes this number here.
We just drew one.
We drew 1 out of the bag, 1 blue, and we didn't put it back. So our probability of blue, then red, we still multiply, but we use this second probability after the first thing happens. So we get 6 over 11. I'm going to reduce 5 over 10. How can I reduce this? 1/2. Good? Yes?
So, is that just a method did R after B?
Oh. Yes. No. We want to find the probability of red. No. This is telling me I want the probability of red after I pick the blue one. So I picked the blue one already. I have to find the probability of picking the red one after I've already picked the blue one. Okay? That's what that means. When we multiply, I'm going to rewrite this as times. When we multiply fractions, we multiply straight across. So this is 6. 11 times 2 is 22. 6 over 22. And I'm going to reduce that fraction, probability blue, then red. Divide everything here by 2. There's 3 out of 11. So I have a 3 in 11 chance of picking a blue and then a red. Does that help with your question? Right? Uh-huh. So let me see if I understand. So you're asking if we roll the die and pick the B and then picked an A, something like that. So we have 3 things happening. No, I'm not understanding your question. Okay, maybe during work time or during tutor time we can get it cleared up. Okay. All right. So dependent events, we still multiply probability, but we have to calculate the second probability after the first event happens. That's the only difference. All right, we have another kind of probability that we need to talk about, and another kind of event. Mutually exclusive. Mutually exclusive events. Anybody have an idea of what mutually exclusive events might be, or what do we mean when we talk about mutually exclusive events? What does mutual mean? Yes. Everybody or together or everything, right? And exclusive means exclude means to separate or to cut out. So mutually exclusive events are cutting out everything. Mutually exclusive events are events that cannot happen together. So an example of mutually exclusive events would be rolling a 1 and a 6 on one die at the same time. A die can only come up one way. I can't roll a 1 and a 6 at the same time. If I pick out from a deck of cards, I can't pick out something that's a 1 and a 2 at the same time. So those are mutually exclusive events. That's things that cannot happen together. The way we write that is we say that the probability of both together, A and B, equals 0. They can't happen together. So what we can do with mutually exclusive events is calculate the probability of one or the other. So we want to figure out, and I'm going to write A and B are mutually exclusive here. Let me move this down. You can leave that written there. A and B are mutually exclusive. The probability of A and B together, both, equals 0. But what we can do is figure out the probability of A or B. The probability of rolling a 1 or a 6 on one roll of a die. Probability of A or B is the probability of A plus the probability of B. For mutually exclusive events, we add. And the clue that's going to, what's going to clue you into a mutually exclusive event is or. Find the probability of this or that. Usually that tells you that you're talking about mutually exclusive events. And means dependent or independent. Or is usually going to mean mutually exclusive. So let's look at an example with mutually exclusive events. We have a bag with marbles again. We have 3 red, 4 blue, and 6 green. We want to find the probability of, in one pick, find the probability of a red or a green. So we're picking one marble. We want to figure out what the probability of that one marble is red or green. If we pick one marble, it can't be both. It can't be red and green. So they're mutually exclusive. So we have to add the probabilities. So I think you're a little ahead of us, but let's calculate the probability of picking a red on our first pick. So how many favorable do we have? 3. How many total? 13. And probability of picking a green? We have 6 favorable. And we're talking one pick, so we're talking the first pick. So what's our total? 13. So the probability of red or green is 3 over 13 plus 6 over 13. To add fractions, we have to have a common denominator, and we add the numerators. So that's 9 over 13. So I'm going to just write these together. Probability of red or green is 9 and 13. 9 chances in 13 that we pick a red or a green on our first pick. So for mutually exclusive events, things that can happen at the same time, we add probabilities. So independent events, dependent events, multiply probabilities, mutually exclusive. Usually when we're talking about an or situation, this or that happening, we add probabilities. We have one other kind of event that we need to talk about, and then we'll be done. Overlapping events. Overlapping just means we have events in common, or have outcomes in common. So an example of an overlapping event would be rolling an even number on a die or rolling greater than 3. Because greater than 3, how many numbers are greater than, which numbers on a die are greater than 3? There are 3 of them, and there are 4, 5, and 6. 4 and 6 are even and greater than 3. So they overlap. There are outcomes of greater than 3, and there are outcomes of even that are in common. 4 and 6 are both even and greater than 3. So they happen in both outcomes. So those are overlapping events. To find our probability, if A and B are overlapping, the probability of A or B is the probability of A plus the probability of B, just like for mutually exclusive events, minus the probability of A and B. We subtract the probability of A and B to get rid of the events that are in common. So with our die, 4 and 6 are both bigger than 3 and even. So if we subtract the probability of that happening, of the 4 and 6, that gets rid of those being counted twice, because they're being counted with a greater than 3 and they're being counted with the even. So subtracting this gets rid of that extra, that double counting. That's why we do that extra subtraction. So let's use our example with our die and find the probability of rolling a number greater than 3 or even. So we roll the die. We want to find the probability of more than 3 or even. So we decided these are overlapping. So we need to calculate the probability of greater than 3, probability of even, and the probability even and greater than. So let's calculate the probability of, I'll write it this way, more than 3. So how many numbers on a die are more than 3? What's our favorable? 3. We have 4, 5, 6. So 3 numbers. How many ways can a die come up? 6. And because I'm adding, I'm going to leave it written as 3 over 6. I'm not going to reduce it. Probability of even. How many numbers on a die are even? 3. We have 2, 4, and 6. So our probability of even is 3 out of a total of 6 possibilities. And now we need probability of even and greater than 3. So how many numbers are even and greater than 3? 2, 4, and 6. And how many total possibilities on a die? 6. So now I'm going to add these together. What I need to do is I'm going to write an extra step here. Probability of greater than 3 or even equals probability of greater than 3 plus the probability of even minus probability of even and greater than 3. That's what our formula tells us to calculate. So I have that this equals probability of greater than 3 is 3 over 6. Probability of even is 3 over 6. And we're subtracting the probability of even and greater than 3, 2 over 6. And that equals, to add fractions, I have to have a common denominator. That's why I didn't reduce any of these. Add the numerators. Add or subtract the numerators. So 3 plus 3 is 6. Minus 2 is 4. 4 over 6. And I'm going to reduce that, divide everything by 2. 2/3. So the probability of greater than 3 or even is 2/3. Subtracting this even and greater than 3, subtracted the ones that we would count twice otherwise. Yes? Yes. So independent, dependent events we multiply. For dependent events we have to find the second probability after the first thing happens. For mutually exclusive events we add. And for overlapping events we add, but we have to subtract the part that overlaps. We've learned how to calculate 4 different kinds of probabilities today. All right, let's go.